Swayam Prabha. Digital India. Educated India.
In the last class, we saw protection paradigms in terms of the apparatus protection or unit protection. We ended the class at directional overcurrent protection, where we use the bus voltage as a discriminant or the polarizing quantity to discriminate the direction of the overcurrent. So now we will move on. We go on to the next higher level of complexity in protection, which is namely the distance protection. Now, in distance protection, we will look at the principle and a very brief introductory concept level discussion on distance protection. So, the basic principle is that the apparent impedance as seen by the relay, we are talking of the voltage as measured by a voltage transformer at the bus and the current through the current transformer in the line or the device that is being protected. So usually it is a transmission line. So, I mean 90% or even more distance relay applications are for transmission lines only. There are other very specialized applications, but they are very few and far in between. So, the relay sees the voltage at the bus and the current through the transmission line and sees the ratio of these two. These are of course phasor quantities, and because it is a voltage by current kind of ratio, it is known as the apparent impedance. We will see when we discuss distance relays in great detail as to how this is compared to the positive sequence impedance of the transmission line that is being protected. If this ratio or this comparison is less than unity, then there is a fault on the transmission line and the relay will issue a trip command. Because it consists of phasor quantities V by I, the resultant is a Z angle theta, where theta is the impedance angle, which can be also written in rectangular coordinates as R plus Jx, which implies that it is inherently directional in nature. You did not give it any other external input. Unlike a overcurrent relay where we needed to give the PT input for it to be able to discriminate the direction of the fault, here there is already a PT input given, and therefore you get a directional sense. Impedance relays and more relays are a few of the relays that are based on this principle. The figure here shows that there is a transmission line AB, and the relay, if we can assume that the relay is placed at the bus A, then if there is a fault on the line AB, then the V by I or the V or the Z apparent will be equal to some m times, if the fault is at a per unit distance m, into the positive sequence impedance of the line. These are two realizations of the relay. One is an impedance relay and one is a Moho relay. Now, the first figure on the left hand side shows an impedance relay. Here, this is the most basic form of application of the distance relay. This of course does not strictly apply to numerical relays, but this is a legacy which has been there with us since the days of the electromagnetic relays. Plot the impedance relay on a Rx plane. Impedance relay characteristics on the Rx plane. This is R, and this is X. It can also be plotted on a VI plane. We will just come back to the Rx plane after we discuss the VI characteristics. because it is V and I. So, say this is the voltage axis, this is the current axis. It can be plotted on the VI plane, and this can be the operate region, and I am sorry, this can be the no operate region, this can be the operate region. However, because it is an impedance, it is more easily visualized on the Rx plane. Now, the most basic implementation is Z is equal to R plus Jx. If I take only the magnitude, or mod Z square is equal to R square plus X square. If you notice, this is the equation of a circle and plotted on the Rx plane with the center as the origin. Okay. So, this is the relay. If it is protecting a transmission line from the earlier example AB, then in that case, if there is a fault on the transmission line, then the impedance locus will be somewhere on the transmission line if it is a bolted fault, and then it is within, this is the no operate region, the region outside is the no operate region, because we are talking of if Z is less than, if Z app is less than MZ line, operate. So, this is the region inside is the operate region, the region outside is the no operate region. Okay. So, because the impedance locus is at this point if there is a fault on the line, it is within the characteristic, and hence the relay will issue a trip command. Now, notice that though the relay, we said earlier that the relay is inherently directional in nature because it is associated with a magnitude and an angle. In this case, we did not use the directional information, or we did not use the angle information, as we are using only the magnitude information. Hence, this relay, this particular realization of the distance relay, the impedance relay, is not directional. You can notice that here in this case, whether the locus of the impedance is in the first quadrant or the fourth quadrant or the third quadrant or the second quadrant, the relay will still operate, or the relay will still issue a trip command. Now, that may not be desired because we are interested in protecting only the line. So, at the most we could restrict the operating area to the first quadrant. So, this relay of course is not entirely useless in that sense. It may be used as a starter relay or some other function, but as a primary protection device for the line AB, it is not very useful. So, to overcome that, if we were to offset this circle by a distance such that it passed through the origin, that is, it lay entirely in the first quadrant, then it would serve our purpose of directional relay also. So, that is what is demonstrated in the second slide, in the second figure rather. If you see the figure on the right hand side, it shows that the circle is offset, so it is known as the Moe relay. If you notice here, the characteristic is almost entirely in the first quadrant. So, we have made sure that the relay will operate only when the voltage lags the current, which is what we saw in the directional relay also, and the directional objective is achieved. So, here the two angles, the angle theta is the impedance angle of the line, which is very close to 90 degrees for EHV circuits, and the angle lambda is known as the torque angle of the relay. These are terms which are been carried over from electromechanical relays, because you had to generate a torque using the two voltage and current coils, so and the relationship between them. So, that is why you had maximum torque angle and a 30-degree relay, 60-degree relay, and all these terms are used in legacy textbooks when you refer to relays. However, for numerical relays, this characteristic can be of any shape. You can imagine that since it can be programmed, you can program the number of points and you can get a quadrilateral characteristic, you can get any characteristic that you want. You can in fact get a characteristic by a quadrilateral characteristic, I mean this. This was the line, say AB. This is a better characteristic than the Moe characteristic, and you can in fact have any kind of characteristic. You can even cut out this part, and since it is programmed, you can have any characteristic that you think is suitable for the line. Now you may notice that we have included a broader area in the first quadrant. We have not just stuck to the line AB. That is because the faults may not be solid faults. You may have say a tree falling over or some other equipment touching the line, and that will have a resistance of its own. So to cater for such possibilities, if there is a resistance say at the end of the line, then you have to go in this direction because this is the R axis. So to cover a broader area, we are covering a bigger area in the first quadrant. Okay, see this kind of area. So this is why you need not only a straight line, but some sort of characteristic which will cover a broader area in the first quadrant. This is what is known as a quadrilateral characteristic. Both quadrilateral and Moe characteristics are used. They are a carryover from the era of electromechanical relays. However, with modern relays, you get different characteristics, but people still persist with both Moe and quadrilateral. So now we will move on to the next level of complexity here. That is the differential protection. The differential protection, as the name suggests, works on a difference principle. That is, the current entering the equipment and leaving the equipment will be different if there is a fault in the system. This can be in terms of magnitude or angle or both. So for this protection, it is applied to transmission lines, to transformers, to bus bars, to generators, to motors. In fact, for any equipment, it can be applied as a unit protection. It is the most precise and crisp form. We will see why of protection that can be applied. So it is as we discussed, it is based on the fact that any fault within the equipment would cause the current entering the equipment to be different from the current leaving the equipment. So you have CTs at both the ends of the equipment, and you compare the two currents. If there is a fault outside the zone, as it is called, then the currents will still be same. They will be high, of course, the fault currents will be high, but they will still be same. So for that, the relay will not operate. So it is, of course, an option which is valid if the equipment, both the ends of the equipment are together, like in a transformer or a generator or a large motor. Also, the rating has to be high because the cost of this protection is high. So it is justified for higher rated voltage, higher voltage and higher rated equipment, generators, transformers, motors. It is also used for transmission lines, for short transmission lines, cables, etc. Nowadays, with the availability of fiber optic communication, it can also be used for longer lines, though the application is not so very common. Okay, so we will see the application to transmission lines. This is the figure. If you observe here, there are some few assumptions which are made that the transmission line is considered as a lumped element in that sense, because you will have otherwise it is a distributed parameter element where you have distributed shunt capacitance and distributed inductance also. But here, for the sake of this discussion, we will consider it as a lumped parameter. We are ignoring the shunt capacitances. In other words, we are ignoring the charging current of the line. That can be incorporated later when we discuss it in a greater detail, and then we will see how to overcome any difficulties that are presented by introducing that quantity. So here we see that IS is the sending end current, or the current which is flowing out of the node A, and IR is the current which is flowing into B. The signs have to be properly adjusted. These are phasors, so they will have a directional component here. So under fault condition, you will see that the summation is non-zero. IS plus IR will not be equal to 0. Under no fault conditions, IS plus IR, the current which is leaving A will be the same as the current which is entering B, because there is no other fault on the line or no other abnormal occurrence of the line. So IS plus IR, notice that they are phasors. IS, if I were to use a phasor terminology, IS bar plus IR bar is equal to 0. If there is a fault, however, on the system, then the IS plus IR summation will not be 0, it will be equal to the fault current, because it will be fed from both the sides, since this is a transmission network. Now, if there is a multi-terminal line, this is what is known as a three-terminal line. They are not very much used in practice. However, they could be used for some applications where there is no space for another line in the substation. Usually what will be done in such a situation is you use the concept known as loop in, loop out. If there is a transmission line passing from A to B, what will be done, and there is a substation C, say a new substation C which comes in here. So instead of, this is what the diagram shows, this is a tapping. However, realize that if the line is tapped, if there is a fault on any one section, then all the, say all A, B, C, all the nodes will lose power. Instead of that, what is done is loop in, loop out kind of concept is used. So what will be done is, the line is brought into C and then taken out of C again, and this is what is done, so that if there is a fault on this section, only AC will go out of service, BC can still remain in service. However, note that this option is a slightly costlier option, because it requires an extra line between the tapping point, say T and C, and also requires some more equipment at the end C. So to avoid that cost, sometimes you may just tap the line, which is what was shown in the figure. Okay, but here, instead of just summing up two currents I1 and I2, you need to incorporate I3 also. So if there is no fault in either of the section, AC or CB, then the summation of the three currents I1 plus I2 plus I3 will be equal to 0. And if there is a fault, it will the summation will not be equal to 0. In fact, it will be equal to whatever fault that exists, IF1 or IF2 or IF3 that exists in the sections. So if there are more terminals, that is even more rare. Of course, for three-terminal lines do exist. We have some in India also. But if there are more sections, then you will have to add that many currents here. So it is simply a kind of application of Kirchhoff's current law. Then we move on to the next equipment, that is the transformer. Okay. So here you see that unlike in a transmission line, a transformer has a winding which will change not only the voltage levels but also the currents. So depending on the transformation ratio, the N1 I1 is equal to N2 I2, the ampere turns will be the same, so the currents will also be transformed. So on the low voltage side, you will have a higher current. So you can't simply summate the currents without adjusting for this turns ratio. So if you can see here, this is of course motivated by the legacy electromechanical kind of relay. You can do without this in the numerical part, which we will see later. Now assume that the transformer has a ratio of 10, which, just for sake of simplicity and just to take an example, assume that the current on the high voltage side is 100 and that on the low voltage side is 1000 amperes. So the CT ratio on the low voltage side, on the high voltage side, say is 100 by 5, and on the low voltage side is 1000 by 5. Why 5? We will see when we study CTs. CTs are generally rated at 5 amperes or 1 ampere. So that is standardized so that the relay inputs can also be standardized. So here, if you remember your dot convention, the current I1 is entering here at the dot. So 5 amperes will leave at the dot as shown. Similarly, if I2 is entering at the dot, then 5 amperes will leave here. So you can see that a circulating current of 5 amperes is being set up, which is shown by the dotted line. Okay. So there is a circulating path here for the circulating current. The actual current, of course, will be I1 into 5 by 100, and I here in this in the right hand side it will be I2 into 5 by 1000. Now if there is a fault on the inside the protected zone by the transformer, the zone is defined by the two CTs here. Then the fault could be due to any reason. There will be a turn to turn short, or a turn to ground short, or a turn to core short, or some abnormal occurrence inside the transformer. Then the turns ratio will be disturbed, and the N1 I1 equal to N2 I2 will no longer hold true. In which case the balance will also be lost, and instead of 5 amperes flowing through the primary side CT and the secondary side CT, you will have some other current which will now spill over through the center path. We will show it here. We have a transformer. This is the CT. Okay, this is I1 which is flowing in the primary. This is I2 which is flowing in the secondary. Okay. Now, if the turns ratio is disturbed, then instead of a circulating path which was earlier set up like this, and it returned like this, what will happen is this current here, which is I1 into say 5 by 100, I am just taking this example here, and I2 into 5 by 100 by 1000 will not be the same. So there will be a difference current here which flows through this path. 5 by 100 minus I2 into 5 by 1000 is equal to some current which will be flowing through this path. Now, if I put a very sensitive current relay here, then even for very small currents, this current is known as a spill current because it spills over from the main path. So this spill current will operate this sensitive relay, and I can obtain a fault indication or a trip. So this is the principle on which a transformer protection differential relay works. Of course, it is not so simple. There will be some other restraining coils here. We will see, because these two currents can't be entirely equal. There is a magnetizing component which has to be fed from either side, and that will not be accounted for in N1 is to N2. So there will be some difference current which will be flowing even if there is no fault on the transformer, and other issues as well. So there will be a restraining component. We will see when we come to this in detail. Now, going back to the transformer protection, here the current element will be set to a value slightly above the no load current value. Of course, this kind of relay, when we used it with electromechanical relays, we needed to account for vector groups and other such equipment in the field. So we needed things like auxiliary CTs or interposing CTs. With numerical relays, that is not the problem. You just simply have to enter the equation and you are done with it. You don't have to worry about whether what side, I mean, whether there is a star delta transformer, so there will be a 30-degree shift in the primary and secondary currents. You can simply program it that way, and that it will take care of the phase shifts, etc. So we move on to the next component. We are not discussing generator and motor protection here. We'll just discuss one more, that is the bus bar protection, and then we will conclude this apparatus protection lecture. The bus bar here is shown as a very simple single bus bar here. Usually for high voltage systems, we will have more bus bars in the interests of reliability. Maybe a double bus bar, or a 1.5, or a single bus bar plus a transfer bus bar. So there are many schemes which are possible. We will discuss when we come to bus bar protection in detail. We are just introducing the concept here. So you can see that here in the left hand side figure, the fault is outside of the bus bars. So if you sum the 5 currents, IA plus IB plus IC plus ID plus IE, the sum will be 0. It is a simple application of Kirchhoff's law. And if there is a fault inside the zone or inside on the bus bar, then IA plus IB plus IC plus ID plus IE will not be 0. It will be equal to the fault current, and hence you can detect the presence of a fault in this case. Now notice that here the CT ratios could be different. Usually they are not very different from each other. In a transformer, of course, they will be dependent on the transformation ratio. Here they will depend on what feeder carries A, B, C, D, E. If say D and E are incomer feeders, they will have a higher current, and A, B, C and E are outgoing feeders, they may have a lower current rating. So depending on what feeder has what function, the current ratings of the feeders could be different, and hence the CT ratios could be different. They could be same, but they could be different as well. That also will have to be accounted for when the differential relay is set. So to summarize, we have seen the basic principles of overcurrent protection, directional overcurrent protection, distance protection for transmission lines, and differential protection for transmission lines, transformers and bus bars, and a few applications. Now we will move on to the next paradigm of protection before we look at other protection aspects in detail. We will look at system protection now in a bit more detail, and then we will move on to attributes of protection. So in system protection, we, unlike in the apparatus protection, we are not talking of individual apparatus. Now the apparatus, imagine that the apparatus that we talked about, transmission lines, generators, transformers, motors, etc., are now interconnected to form a system, a power system or a network. And here it is essential that the generators operate synchronously there, so that power transfer is possible. So to make sure that the generators that are going out of out of step due to some post fault occurrence, usually this is not the system instability is not the direct result, but a follow up of the fault occurrence on the system. So to prevent generators from going out of step or operating asynchronously with the other generators, system protection relays or system protection measures are used. We will discuss a few of them in this class. Okay, before we go on to the system protection, background of system dynamics is necessary. You are aware that the whole power system can be described as a set of differential and algebraic equations, and to do a transient analysis, you need to use these models of the transmission system of the power system, and then solve it by EMTP or any other transient analysis program. Now, this is for the transient analysis of the system. We are not talking of transient stability here. That post-fault transient stability can be determined by stability studies. Unlike the transient model, the power system model for transient stability studies can be a phasor model, or rather is a phasor model. You can use R plus Jx kind of models for the transmission line, or R plus Jx and B by 2 models for the transmission line. And what is changing in a transient stability program is the phasors. We are not dealing with L di by dt's or C dv by dt's. That is done only in the transient analysis program or EMTP kind of program. So if you look at the time scales, this is how it looks like. The electromagnetic transients like lightning and switching, etc., are very fast transients. The frequency is very high. The time period is very low and the frequency is very high. So because we are talking of traveling waves and L di by dt's and C dv by dt's here. Later, as the synchronous machines have not yet reacted here. So our relays have to operate in this time zone, or just after the transients have died down, and towards the end of this time period, that is towards around 100 milliseconds, the synchronous generators will begin to react, because they don't react instantaneously because they have a high inertia. If you remember, the 2h by omega s d2 delta by dt2 is equal to Pm minus P. So that h, the synchronous machine inertia is quite large and it takes time to react. So because it takes a higher time, the frequency will slightly be lower than the electromagnetic transient frequency. So here this is the time period which is shown by 2, that is about 100 milliseconds to 1 second. Even slower than that are the electromechanical kind of governors, etc., that are present on the synchronous generators. After that, you have even slower dynamics like load frequency control, and the loads start reacting after that. And the last is, of course, the boilers. If you see, a boiler is a huge piece of equipment for larger synchronous machines, and it takes a long time. The steam, etc., build up will take a long time. So that is the slowest. That is in minutes or even hours and sometimes. So our relays have to react at around the 100 millisecond mark. What is happening during the system instability? Now this, as we said, is a result of some post-fault occurrence, and what is essentially happening is that Pm minus P, that balance is disturbed, and because of that, the machines will start accelerating or decelerating, which will imply a change in frequency. So to detect that, and why is that a problem? Because the system, the machine may go out of synchronism, and power transfer may not be possible. There are large changes in voltages and currents, etc., which may damage the machine. So to prevent that, frequency relays, power relays, vector shift relays are the kind of relays that are used. Pm minus P, as we said, that balance is disturbed, and because the machines will start accelerating or decelerating, the frequency changes, and that can be detected by either under frequency or over frequency relays. If the generation is less than the load that is present, then the machines will slow down and the frequency will start dropping. If on the other hand the generation is more, then the machines will speed up and there will be an over frequency occurrence in the system. The machines, the synchronous machines, the turbines that are associated cannot operate beyond a particular envelope. So to prevent the damage to the machines, either an over frequency or an under frequency relay will be used, or multiple relays will be used. Okay, so we will see an example here of a system where under frequency relays are used. Now, you would ask why multiple relays are needed. You could have only under frequency relays or over frequency relay, only frequency relays. But what happens is frequency, as you would know, is a lag measure. By the time the lower limit of the frequency is reached, it may be too late to take any action or to save the system. The machine may still go out of synchronism. So to avoid this, what if you had some advanced information, like the frequency is falling at a very rapid rate, though it is 49 hertz now or 49.5 hertz now, it could reach 47 hertz very fast. That information can be got from df by dt, or rate of change of frequency. So if you see that the frequency is at a certain level and it is falling very rapidly, you can take the action in advance to prevent this. So that is why we use rate of change of frequency relays. Again, it may so happen that though there is a fault and the system may head towards instability, the load generation balance may not be very different, or the PM and PEs may not be very different. So the differences could be minor and the change in frequency could be at a very, very slow rate, but you still want to avoid that. So that could be checked by using under voltage relays or reverse power relays. The power direction could reverse, because if there is a fault outside the area or outside the plant that you are protecting, the power direction which was earlier into the plant or into the area may reverse and your generators may start exporting. We will see an example shortly. And because of that, you could have a problem in the slightly longer run. So to avoid that, you can use relays like reverse power relays or under voltage relays. So I will show you an example of an actual system, what kind of relays that are used. So we will see an example system also. This is an example of a plant which has the local loads here, and it is also fed from the utility. They have a captive generation which is of the order of 100 megawatts. The loads are divided here. You can see there is a local kind of load which is maybe an essential load. It is not mentioned here, but assume that it is an essential load of 50 megawatts. There are other loads of 50 megawatts and 100 megawatts on the same bus. So because the generator power is 100 megawatts, your own captive generation is 100 megawatts, you have to import 100 megawatts from the utility, which is shown by the green breaker here, which is in the closed condition. Now imagine that there is some fault on the utility side, and due to which this breaker also opens. What will happen is, you can see that this breaker has opened. So 100 megawatts which was flowing in from the utility side is suddenly not available. So your generator, which was earlier providing 100 megawatts, has to now cater to loads of not only 50 megawatts, which is the local load, but also the other 150 megawatts. So a 100 megawatt generator will be now loaded to 200 megawatts. So this is definitely not sustainable, and it will start slowing down to a point where it will be tripped by its own under frequency relays. To avoid that and loss of power to the entire plant, you can provide a frequency relay R, which is shown here, or maybe a frequency relay at the 100 megawatt load to trip out that load, so that this 50 megawatts plus the other 50 megawatts, depending on what load is essential, what load is non-essential, what load is critical. This has to be done before. You can't do it when the fault has occurred. The whole system has to be designed before. That is known as an islanding system. We will see when we come to that point. And here that this frequency relay R will trip, and the generator here 100 megawatts can comfortably supply that 50 megawatts. There will be some control action required by its governor, of course. If the other 50 megawatts were also to be brought in circuit, then that 100 megawatt generator will supply 100 megawatts, and stability will not be an issue. So this is one kind of system. We discussed under frequency and rate of change of frequency relays because frequency is a lag measure, so you need some warning in advance, which can be provided by rate of change of frequency relays. Okay, we discussed this. This speeds up the islanding decision or the isolation decision. You have information available in advance, and the load generation balance can be maintained in such a case. So that is why this kind of protection is used. Imagine that a power system or a interconnected system is a complex system, and there is not only one kind of occurrence that can happen here. So that is why you have to cater to various kinds of happenings. So that is why sometimes the load generation balance may be disturbed, sometimes it may not be disturbed due to a fault also. So to cater to all these kind of eventualities, you have a multiple variety of protections to choose from, which we are discussing here. Okay, so we will discuss an application of the under voltage relay and the reverse power relay with an example. So as we mentioned, if there is a fault on the grid very close up to the plant, the voltage will drop. The load generation balance may not be disturbed, may or may not, depending on the impedances and how the system is configured at that point. The load generation balance may not be disturbed, so the frequency may not fall, but you don't want to keep feeding the fault, and in such a condition, an under voltage relay will be helpful. Here, if there is a power direction reversal, then a reverse power relay is also used, and this is quite frequently used. We will see this with an example. This is best demonstrated by an example. Okay, this is the example here. This kind of setup is quite common in large industrial plants, refineries, etc. Here there will be a plant generator here, and there are other loads which are being fed outside by the utility. This is similar to the utility which we saw earlier. Utility could be anything, so your Discom or Transco, depending on what voltage level the plant is being fed at. Then here at the interface there will be a reverse power relay. This could also be ANDed with an under frequency relay. So if the reverse power and under frequency occurs, then there will be an islanding decision. It could be a pure reverse power relay also. So in this case, this is the normal operation of the plant, where the utility supplies some load, some part of the load, and the generator also supplies a part of that load. Now, if there is some fault on the utility side, then what will happen is the power flow will be reversed. The utility side breaker will open, and because there are loads which are there outside the plant also, which are not being fed now, this generator, the plant generator, will start feeding those loads, and it will get overloaded, and because the load generation balance cannot be maintained, it will eventually start falling back, and then will trip on under frequency. So to avoid that, you have already noticed the change in flow direction, power flow direction. So this can be taken advantage of, and you can trip the plant interface and then save your plant from being tripped altogether. Because if you lose the in-plant generation, then you don't have the utility, then your plant can no longer function. So to avoid that kind of occurrences, we use a reverse power relay at the interface and trip. We could also have used an under frequency relay, but that depends. As I said, that depends on the load generation balance, etc., as to which relay will operate first. I will show you an example of a scheme which was used in actual practice. Here you can see that there is a dF by dt scheme. These are the ratings here, 48.5 and 1.5 hertz per second. There is a second stage, which is an over frequency stage, 51 and 1.5 hertz per second. There is an reverse power and under frequency scheme, which is if the plant starts exporting greater than 10 megawatts, then and the under frequencies is less and the frequency is less than 48.5, then a trip command is issued. And sometimes, as we said, that the load generation balance may not be disturbed so much. So to account for that, there are pure under frequency and pure under voltage scheme. So this is the islanding scheme which was used in actual practice. And here, after using that scheme, you can see here, if you notice here, that if you notice this point, that the frequency had started falling, but after the under frequency scheme operated, the frequency profile has improved. So this was about the islanding. Now, only one part remains, that is the in the system protection, that is the lightning protection. Now, lightning protection strictly is not a relaying function. You can't protect a system from lightning by using any kind of relays. The only lightning protection devices which can work are um, nonlinear nonlinear arresters or nonlinear resistance kind of devices, which are basically ZNO varistors, which are known as surge arresters. These are applied in the system. These operate in the very early part of our. If you see here, they operate at the in the electromagnetic transients kind of thing. The relays will not be able to react in the earlier, because the relays start reacting only towards the 100 millisecond kind of mark. So, no relays can be used to protect against lightning. The lightning over voltages can be classified into three parts. One is the lightning over voltages which are induced due to a lightning strike in the vicinity of a we are talking of transmission lines here, because the lightning, usually a substation is well protected. So, the likelihood of a lightning strike is more on the transmission line. It will strike the transmission line and a travelling wave will be set up and enter the substation. There it will need to be protected. So, the lightning over voltages are of three types. One is the induced over voltage due to a lightning strike in the neighborhood of a transmission line. Then there is a over voltage which can occur due to back flashover. What is a back flashover? We will just shortly see. We will not discuss this in too much detail because it is not a part of this course, but just for the sake of completeness we will discuss this. And then there can be over voltages due to shielding failures. So, these are the three kinds of over voltages that are possible. I will just describe them in very brief detail. You are aware of how a transmission tower looks like. We will just take a single tower for the discussion here. There is a shield wire here which is on the top of the transmission wire. Some transmission towers will have two shield wires. Then there are cross arms on which there are. This is, I am drawing a double circuit tower here. You could have a single circuit tower also. Okay, this is a steel lattice structure here which is grounded. Okay, and then there are insulators. These are insulators, and then there are conductors which are this round part is the conductor. Okay, so the first kind of over voltage is there is a lightning strike in the neighborhood, due to which over voltages are induced here because of the proximity here, and then a travelling wave which is set up travels on the transmission. This transmission line, of course, will travel from one substation to another. I have just drawn a cross section. So, the second kind of over voltages is the lightning strikes the ground wire here. Okay. Now, when it strikes the ground wire, a travelling wave will be set up. One part will travel towards this tower, the other part will travel towards the next tower. Okay. Now, when it comes to the tower here, it will encounter a discontinuity. The earth wire has a surge impedance of around 100 ohms or so. The tower has a surge impedance of around 200 ohms. So, it will encounter a discontinuity, and a part of this, depending on the, say, if Zg is the surge impedance of the ground wire and Z line is the surge impedance of the this is the reflection. Okay, R say is then this is the reflection coefficient here. Depending on how much is reflected and how much is refracted, a part of the voltage wave will come here on the transmission line. Till it will travel down the transmission line till it encounters another discontinuity here, and this grounding resistance, that is why we say that the grounding resistance should be as low as possible, and certainly less than 10 ohms. So, this is what is specified in transmission line specifications. You need the grounding resistance to be less than 10 ohms, and very near to the substation, sometimes it is even specified to be less than 1 ohm. Okay. So, here at this discontinuity point, the reflection coefficient will be Rg minus ZL divided by Rg plus ZL. Okay. So, if this is 0, then it will be just -1 and no reflected wave will be set up. But if it is non-zero, then there will be a reflected wave which is set up, and this happens, this wave will travel back and forth till the voltage at this point, or the tower voltage exceeds the breakdown voltage of the air here, okay. And then there will be a flashover from the tower cross arm to the conductor. That is why it is known as a back flashover or BFO. Okay. Once that happens, and a traveling wave will be set up which will travel to the substation and may damage the equipment there. Okay. Shielding failure is the third kind is the earth wire will not, or the shield wire will not come into play, and the lightning will strike the conductor directly. This is also known as direct stroke. Okay. So here the lightning strikes the conductor directly, and that traveling wave will travel into the substation and could damage the equipment in the substation. The substation equipment are designed to withstand a certain voltage, which is known as the basic insulation level. For 132 kV, it is of the order of 550 kV peak or 650 kV peak. For 220 kV, it could be 950 or 1050, and so on and so forth. So if your over voltages due to lightning exceed these values, then your equipment could get damaged. The lower voltage, the lower of the two, is generally used for transformers, as that is a costly equipment. Okay. So to prevent that from happening, we use equipment like surge arresters. These are ZNO discs which are stacked depending on the voltage and the current ratings. They could be stacked in series and parallel, and this is such that as normal voltages they will not conduct, so they are sealed off, and when a lightning stroke occurs due to the high voltage, the surge arrestor will conduct and divert the lightning stroke, thus preventing it from reaching the substation equipment. Of course, shielding by proper earth wires and proper earthing. We saw why these are important. Because shielding is of course important, because otherwise you will have strokes directly to the earth wire, to the conductor, I'm sorry. And proper earthing is also important, because if the earthing is not proper and the tower footing resistance is high, a larger part will be reflected back, and the chances of back flashover are increased. So to avoid that, you should have proper earthing with a proper low value of tower footing resistance. Here, this is known as the shielding angle. If this is the tower top, then usually it is designed such that, I'm sorry, this is a larger value. It is so this is the first cross arm. Then it is designed such that this angle is about 30 degrees. Okay, so for about 30 degrees, it will provide this is known as a shielding angle. Okay, and if there are two peaks, some towers, if you have noticed, may have two peaks, and then there is a transmission tower, and then usually this 20 degree shielding angle is provided. So to summarize, we saw the power system dynamics. Saw in very brief at the concept level. Then various system protection relays like under frequency relays, rate of change of frequency relays, reverse power relays, under voltage relays, and finally we concluded with the lightning protection, which now concludes the discussion on the system protection aspects. In the next class, we will see attributes of protection and also get started with current transformers, which are the input transformers to the relays. So, thank you.